Okay, today we're going to have a lesson on arithmetic sequences. I teach this a little differently than some of the curriculums do. I kind of have a simplified version that makes sense to me. So you may have a teacher that teaches this differently, but here's my version of it. First of all, we have to determine whether a sequence of numbers is actually an arithmetic sequence. So let's look at this numbers here. We have to ask ourselves, how do we get from a 12 to an 8? You would subtract 4. How do you get from an 8 to a 4? You subtract 4. And how do you get from 4 to 0? Subtract 4. What we are looking for this to be an arithmetic sequence, is for there to be a common difference. That means that we are adding or subtracting the same number. Since each time we are subtracting 4, this is indeed an arithmetic sequence. And then it asks us to find the next 3 terms. So we would continue to add a negative 4. So the next 3 terms would be negative 4, negative 8, and negative 12. In this example, when you look at it, how do you get from a 1 to a 4? You add 3, then we add 5, then we add 7. This is a pattern, but it is not an arithmetic sequence because you are not adding or subtracting the same number. So this, we could not use the equation that we're using today on this because this is just a pattern, but not an arithmetic sequence. On this one, to get from a negative 4 to a negative 2, we add 2, then we add 3, then we add 4. Again, this is a pattern, but it is not an arithmetic sequence. So right now we're just seeing if they are arithmetic sequences and if we can use the equation that we're using today. Here we have from negative 2 to negative 31, you have to subtract 9. Sorry, I had to think there for a minute. From negative 31 to negative 40, again, you're subtracting 9. And from negative 40 to negative 49, again, you're subtracting 9. Here we see the arithmetic sequence. You are adding or subtracting the same number. So we could carry on the sequence by subtracting 9 each time, which would be a negative 58, a negative 67, and a negative 76. To understand the formula that we're using today, we're going to just look at a couple of things. First, if you count by 5s up to 40, you would have 5, 10, 15, 20, 25, 30, 35, 40. But what if I ask you to count by 5s, but instead of starting on 5, I want you to start on 3? Then you would count 3, 8, 13, 18, 23, 28, 33. This is an example of an arithmetic sequence where you're counting by 5s, but you didn't start on 5. You started on a number that was actually 2 less than 5. And that's the kind of thing we're going to be looking at today. So when you see a chart like this term number at the top, all this means is that this is the first number of the sequence. This is the second number. This is the third number. They're basically stating the obvious here. We know that's the first, second, third, and fourth terms. So here are the numbers we're looking at. So first we're going to look to see if it's an arithmetic sequence. To go from 6 to 7, that's a plus 1. 7 to 8 is a plus 1. 8 to 9 is a plus 1. So each time we have what we call a common difference, which means we're adding or subtracting the same number, and that is adding by 1. We're counting by 1s. Now, we're counting by 1s, but did we start counting on the number 1? Did we go 1, 2, 3, 4? No, we started on a term, which was 6. There was actually 5 more than where we're counting by. That's going to be the 2 questions that we need to ask in order to come up with our equation. Since we are counting by 1s, when we write our equation, we're going to write 1 times whatever term it is. Then, so if it's the first term, you multiply it times 1. If it's the second term, you multiply it times 1. But we didn't start counting on 1. We started counting on a number that was 5 more than 1, so we're going to put a plus 5 here at the end. So that is our equation. course, the 1 can be invisible. Then when it asks for you to find the 12th term, you simply plug that in to n, and you have 12 plus 5 equals 17. You will see questions like this on your ACT test, and this is an easy way, fast way to come up with the answer without sitting there adding it over and over again on your calculator. Here's another example. If we look up here, we're counting 4, 8, 12, 16. That's adding 4, adding 4, adding 4. So we have a common difference because each time we were adding a 4, which is a positive 4. Then we ask ourselves the question, what are we counting? We're counting by 4s, but did we start on the number 4? We did. So we do not have to add or subtract anything. So our equation is just simply 4 times whichever number you want. If you want the 20th term in the sequence, you just go 4 times 20. And it would be 80. In this example, we're counting 7, 10, 13, 16. Each time we are adding 3, so we call that our common difference. It's a positive 3 since we're adding by 3. So that's going to be the first part of our equation, 3n. Now we ask ourselves the second question. Did we start counting on 3? Did we go 3, 6, 9, 12? We counted by 3s, but we actually started on 7. And this number is 4 more than 3. So at the very end of our equation, we want to write plus 4. So we're counting by 3s, but we didn't start counting on the number 3. We started counting on a number that was 4 more than 3. That's how we write our equation. Now to find the 15th term, we simply plug in 15 to the equation. 3 times 15. Then we add the 4, and that would be 49. Another example, 11, 22, 33, 45. Each time we are adding 11. So yes, this is an arithmetic sequence. Since we're counting by 11, when we write our equation, we know we're doing 11 times whichever term number we want. Second question we ask ourselves, we're counting by 11, but did we start on number 11? Yes, indeed we did. So that would be a plus 0, which is unnecessary. So our equation is just t equals 11n. To find the 25th term, all we have to do is plug in 25 to the equation, and it would be 275. Next example, when we're counting 7 to 10, that's adding 3, adding 3, adding 3. So yes, indeed, we have an arithmetic sequence. To write our equation, since we're counting by 3s, we know we take the term number and multiply it times 3. But did we start counting on 3? Did we go 3, 6, 9, 12? Again, we started on 7, which was 4 more than 3. So there's our equation. Now to find the 20th term, we're just going to fill in the number 20 to the equation. And let's see if we can get our smart board figured out here. I don't know what that is. I don't know how to fix it. So we'll just see if it'll, there we go. There's the equation. Plug in 20, and it would be 64. Now this example is a little different because this time we're counting backwards. So how do you go from a 5 to a 2? You're subtracting 3. To go from 2 to -1, you're subtracting 3. And that pattern is going to continue. So when we write our equation, since we're subtracting 3, we're going to start out with a -3n. So you're saying to yourself, I'm counting by -3s. I'm going backwards by 3 each time. Second question you ask yourself, did I start counting on 3? Well, no, I actually started on 5. Well, how far is 5 from -3? If you think about a number line, how far is -3 to 0? Well, of course, that's 3. How far is 0 from 5? Well, of course, that's 5. So to figure out how far -3 is from 5, all you have to do is add the absolute value of those two terms, and it's 8 away. So it took 8 numbers away from -3 to 5. So we started on a number that was 8 more than -3, so we say plus 8. Now we plug in 22 to the equation, and we have negative 3 times 22 plus 8. You do your multiplication first because we always follow our PEMDAS, or our order of operations, and we get negative 58. Here we have 1 to 5, we're adding 4. 5 to 9, we're adding 4. 9 to 13, we're adding 4. So our equation is going to be 4n. Second question we ask ourselves, we're counting by 4s, but did we start counting on the number 4? Well, no, we started on 1, which is a number that is 3 less than 4. So we put minus 3, saying that no, we didn't start on 4. We started on a number that was 4 minus 3, which was 1. Now that we have our equation, we're going to plug it in, and the number would be 353. It's a lot easier to use this equation than go plus 4, plus 4, plus 4, 89 times. Okay, again, on this particular one, you see that each time we are subtracting, we're counting backwards by 11. So since we're counting backwards, we say we have a negative 11n. Second question we ask ourselves, did we start counting on negative 11? Well, no, we started on 121. Well, how far is negative 11 from 121? Again, you have to think about the absolute value, because negative 11 to 0 on a number line is 11 places, and from 0 to 121 on a number line is 121 places. So altogether, you add together those absolute values, we started on a number that was 132 more than the negative 11 that we are counting by. So here's our equation. Plug in the 10th term, and our number would be 22. Good luck on arithmetic sequences.